In the 50 years since Sputnik first flew to space, the media world has changed beyond recognition. Suddenly, satellite television allows us all to watch the same event at the same time.
Satellite television came of age, probably with the man landing on the moon in 1969.
That's one small step for man.
It was then clear that only because there was telecommunication satellites, it was possible to distribute this signal, which was arriving from the moon in the United States, to the rest of the planet.
In a matter of days, the eyes of millions will be on South Africa for the World Cup, and the TV satellites will be buzzing.
If somebody scores a goal in Johannesburg, before we can see it in Madrid, the signal will have to travel to the satellite 36,000 kilometers and back again. This takes 250 milliseconds.
Even with encoders processing the pictures, the viewer at home is just a few seconds behind the action. We've come a long way in just a few decades.
In the 1970s, the satellites were very small. Today we are talking about satellites of the 5, 6, 7,000 kilos with 50 to 100 channels, where you can put in a single satellite probably 500 television programs. And altogether, in space, at the moment, there are about 300 satellites, and on those 300 satellites, there are 25,000 programs.
Switch channels to the south of France. This clean room in Cannes is where a quarter of the world's telecom satellites are made. The central component is a carbon fibre tube.
You could call that the skeleton of the satellite. It's the base on which the rest of the satellite will be built.
There's only one way up to space, and that's strapped to the top of a rocket.
It's pretty amazing. The equipment on the satellite vibrates and faces levels of almost 100 G in acceleration. In terms of noise, a rocket makes more than 1,000 times more noise than a large aeroplane. So there really are very significant stresses.
40% of the telecom satellites produced worldwide are made by European manufacturers. In this room, the engineers are testing a reflector dish to make sure it reaches an exact geographical area.
The reflector's not broken. It's deliberately shaped to make sure that the beam can be focused on a very precise zone.
The satellites are folded up into a container before being shipped off for launch. This one is all ready to go, wearing the protective wrapping that it will keep in orbit to stop harmful sunlight damaging the instruments.
All the layers are made by hand, drawn up one by one, stitched by hand, and then mounted on the satellite and fixed on with Velcro or stitched together.
Once launched, a telecom satellite has to be reliable, as it's expected to last 15 years in orbit. This in a harsh vacuum where temperatures range from minus 150 to plus 150 degrees centigrade. Back on Earth, the operators keep a watchful eye on their fleet. Engineers here at Hispasat's control center near Madrid are constantly monitoring the firm's 6 satellites as they follow what's known as a geostationary orbit.
If you want to receive signal from a satellite, and you want to have a fixed antenna, and since the Earth moves with a periodicity of 24 hours, which is a day, the satellite has to move synchronous with the Earth. And there is only one orbit is in the plane of the equator, 36,000 kilometers from the surface of the Earth. This orbit allows the satellite to move synchronous with the Earth. This is the geostationary orbit.
Roughly every 2 weeks, the engineers fire the booster rockets on the satellites to adjust their path. That's because they're constantly being pushed and pulled in different directions.
There is a number of physical effects. One of them is the pressure of the sun. The sun produces radiation. The radiation has energy, but also has mass. And the radiation hitting against the solar panel produces a torque. And then the satellite tends to move. But also because the Earth, theoretically, is a perfect sphere. Well, it is not. It's a geoid, and the geoid has deformations. So not in all the places of the space you are having the same gravity. In addition, the moon is changing the gravity with respect to the satellite. The result is that all those signals combined produce a drift of the satellite position, and that's why it has to be corrected.
A quick zap to the Netherlands, where engineers are developing the TV of tomorrow. The European Space Agency's Marco Sartori is researching three-dimensional television. So how does it work?
So human beings have two eyes, therefore we need two pictures, one for the left eye and one for the right eye. We send both pictures up to the satellite, they come down to the television, and the television shows them merged. But when you put on the glasses, you get the 3D wow effect.
Marco's testing the system from both sides, not only to see how users like the picture, but also how the picture can be distributed by satellite. For the moment, the two parallel images are sent up to space on one HD channel, but ESA's also exploring other technical solutions. This work could help to define future 3D TV systems and the standards that could be adopted across Europe.
What's very important is to be able to optimise the bandwidth that we use from the satellite. The satellite's an extremely scarce resource, so we want to be sure that we're optimising every last bit that we can get from our satellites.
Alongside 3D TV, another key trend is personalisation.
One thing that is impacting is IPTV, television à la carte. There are new satellite television systems that allow you to focus the signal basically to a spot that only covers the area where the customer is requesting. Those satellites are able to multiply their capacity by 50 times.
More channels, personalised broadcasting, 3D TV. Plenty of reasons to keep your satellite dishes trained on the sky.